Hello and welcome to Common Core Geometry by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 2, Lesson number 3 on reflections. Now, this is the third lesson in this unit, and what we're doing at the beginning of this unit is really taking a good look at each one of the types of rigid motions. Those are transformations in the plane that don't change the size or the shape of the object that's being transformed. In the last lesson, we took a look at rotations, and if you didn't watch that lesson or you haven't had it yet, it would be a good idea to go back and take a look at it, because I'm assuming that you have seen that one. But let's jump into reflections, because that's another type of rigid motion. All right, but let's recall what the definition of a rigid motion is. A rigid motion, any transformation that does not change the size nor the shape of an object. All right, doesn't change the size, doesn't change the shape. Let's take a look at this first exercise, because this is all about understanding the properties of a reflection. Exercise number 1. In the following diagram, triangle ABC has been reflected over line M to produce triangle A', B', C' as shown. The diagram is drawn to scale. Use tracing paper to verify that this is a rigid motion, i.e. that the two shapes can be made to coincide. All right, I love tracing paper. I wish I could literally use it on this screen. But what I need you to do now is take your tracing paper, trace out that triangle, and do whatever you can to get it to overlay on that triangle. Take a moment to do that. All right. Now, I don't have tracing paper, but what I did was I took the triangle and I just made an image of it in red so that we could sort of tell the difference between it. Let me see if I can bring this guy out to the front. That way we'll always be able to see it. Now, right now, if I bring it over here, it doesn't seem like it's kind of going on top of it, and that's because it's been a reflection. I need to literally flip this thing, and I could actually flip it just about any way I want, and then I'll have to rotate it a little bit, and what I find then is that it lies right on top of it. It's definitely a rigid motion because it hasn't changed the size or the shape of the pre-imaged triangle. Anyway, I'm going to throw that red one out of there, and we'll move on to part B. Draw inline segment A', B, B', and C, C'. What angle do these segments make with line M? All right, so let's draw those in. I'm going to grab my line utility. We've got all of those. We've got them drawn in. What angle do those make with line M? What does it look like? If you need to, pull out your protractor and go ahead and measure the angle. All right, well, let me get back to my pen. If you said it made a 90-degree or right angle, you would be correct. So in other words, this is 90, this is 90, and this is 90. All right, so this is interesting. One thing that happens when you reflect a point across a line is that when you connect the point to its image point, that line segment is perpendicular to this line. Let's take a look at another important property. In letter C, it says, mark the intersection points of A', B', and C' with line M. All right, so in other words, let's mark these points. All right, what do we know about these? Now it says what is true about these points relative to the line segments A', B', and C'. So in other words, is there anything that's special about those points? Anything special about them whatsoever? Well, if you said that they were the midpoints, if they were the midpoints of A', B', and C', then you'd be correct because they are. So let's really think about this for a second. It's kind of cool. When I take a point and I reflect it across a line, right, then what happens is it goes the same distance on one side of the line as it is on the other side of the line, and it moves perpendicular across the line. All right? It flips across the line. That kind of holds with what we generally know about reflections, just from our common everyday experience. Let's take a look at their technical definition. Again, technical definitions can be fairly challenging in mathematics, so I want you to take a moment, pause the video, and read through the technical definition of a reflection that's up on the board and it's on your worksheet. All right, let's take a look at it. Reflections. We can reflect a point A in the line M. Notice that kind of terminology. Reflect A in M to produce A prime by using the following. If A does not lie on M, then locate A prime, so A doesn't lie on M. Locate A prime on the other side of M such that segment A prime is perpendicular to M, and A prime intersects line M at its midpoint. All right? Again, we flip the point across the line such that this line segment is perpendicular to this one and that A is the same distance on one side of the reflecting line as it is on the other side. Now that's for a point that is not on the line of reflection. What about reflecting a point that is on the line of reflection across that line? Let's take a look at part B, or number 2. If A lies on M, then its reflection is simply itself. In other words, if I have some line and I have some point on the line A, right, if you think about this for a moment, if I flipped all of this, that point would remain on that line. So any points that lie on a line of reflection don't change their location when they're reflected in that. Let's take a look at this technical definition of a reflection by taking a look at a GeoGebra widget. All right? In this particular diagram, we've got line BC and point A. And what I'd like to do is I'd like to reflect point A about that line. So I'm going to choose A, choose the line, and there's its image point. Now, what did we learn about that? What we learned about it was that if I connect these two, all right, and let me just mark a point at the intersection, because that was important, right? If we did that, then what we found was that this angle would be 90 degrees, and it is. And what we also found was that this length and this length should be the same, and they are, right? So what we can see in this case is that it's very, very simple. The idea, generally speaking, with a reflection is that wherever the point is, you would walk perpendicular to the line of reflection, and then you'd walk the same distance back out. Works the way that you would think, well, quite frankly, a mirror does in a reflection. Very, very simple. Let's move on and work a little bit with reflections. All right, take a look at exercise number 2. Let me read it for you. Exercise number 2. What properties of a figure would remain unchanged, in other words, are preserved, when a figure is reflected? Now this is important, okay? A reflection is a rigid body motion, and therefore there are 2 primary answers to this question. See if you can remember what they are. All right. Well, because a reflection is a rigid body motion, number 1, it's gotta preserve distance or length. In other words, when I reflect line segment AB across this line M, if AB is 4 centimeters, its image is 4 centimeters. But there's another property, right? And the other property of all rigid body motions is that when I reflect an angle across that line, the measure of the angle won't change. If it's a 26-degree angle here and I reflect it across that line segment, it's a 26-degree angle there. All right, make sure you know those 2 properties. They're true of every type of rigid body motion. Let's move on to the next one. Okay, exercise 3 puts us back in the coordinate plane, where reflections are pretty easy, especially if you're reflecting across the x and the y axis. And we'll talk about why that is in just a moment. But let's take a look at this exercise. Exercise number 3. On the grid paper shown, segment AB has been graphed with endpoints at A, 4, 7, and B, 8, 1. We'd like to see what happens when the segment when we reflect it in the y-axis, followed by a rotation of 90 degrees counterclockwise about the origin. All right, great. In letter A, it asks us to determine the coordinates of the endpoints of the new segment after both of these transformations. Label it A double prime, B double prime. Well, we have a series of rigid body motions right now, the first one being a reflection in the y-axis, and the second one being a rotation by 90 degrees. Let's reflect the two endpoints, all right? When we take a look at A, when we reflect it in the y-axis, we simply need to go into the y-axis perpendicular, which means horizontally. That's 4 units, so we would come out another 4 units, and we would end up right here, all right? That being said, I'm going to erase that so that it doesn't kind of get all messy. That means A, which is at 4, 7, initially gets mapped to A prime at -4, positive 7. Eventually we'll have a little arrow there for A double prime. Let me mark this as A prime. All right, B, likewise, since it's 8 units to the right here, it will end up being 8 units to the left here, and that'll be B prime. So B, which is at 8, 1, will get transformed to B prime, -8, 1. All right, let's draw that line segment in. I'm going to just kind of hand sketch it in. That's good enough. Now for the tricky part. We need to rotate by 90 degrees, and that tends to be the hardest one for students. It's one that sometimes students will even memorize some kind of rule for because it's kind of tricky. I've always found the same thing, which is I'm just going to take my graph paper and rotate it 90 degrees counterclockwise and see where they end up falling. In order to do that, I actually have to group this object together right now, something like this, hopefully. Am I going to get it all? I did, wonderful. All right, let's group these together, and now that'll allow me to rotate 90 degrees counterclockwise about the origin, like this. Now what I can say is that A double prime is going to be at -7, -4. So this now is A double prime. And B double prime, oh, I don't know what that was. Let's try that again. And B double prime is going to be at -1, -8. Let me step back here for a second. Again, I've taken my graph paper and I have literally rotated it 90 degrees counterclockwise. And then I've read off the coordinates of that point. I'll rotate it back the 90 degrees and I'll plot A double prime, B double prime right now. All right, I'm going to rotate this back by 90. A double prime now is at -7, -4. B double prime is at -1, -8. And there's my line segment. Okay? Are AB and A double prime, B double prime the same length? Use a ruler or tracing paper to justify your yes/no answer. Apparently, I don't have either on here. All right? But why don't you go ahead and use either tracing paper or a ruler to take a look at this. All right. And what you'll find, I'm not going to spend the time to bust out our ruler right now, but as the answer is yes. In other words, if I took a ruler, or even better yet, I just took tracing paper and I traced that segment, what I would find is that it would lie exactly on top of that segment, right on top of it, right? And letter C, very important, why does your answer from part B make sense? Why does your answer from part B make sense? In other words, why should it be the same length? Think about what you would write down for that. Yeah, do you have something? Okay, it makes sense because both reflections and rotations preserve length. So, when you put them together, they will also preserve length. Or I'll say their combination. It's actually called a composition, but their combination, wow, just barely fit that, will also preserve length. Period. Right? And it makes sense, simply because when I took AB and I reflected it across the y-axis and got A prime, B prime, that would have to be the same length as that one. Then when I took this and I rotated it 90 degrees to get this one would have to be the same length as that one. So if this is the same length as this, and this is the same length as that, well, then these two have to be the same length. They simply have to be. All right, let's keep going. Exercise number 4. You ready for this one? This is kind of cool. Now, we're going to get a result in this particular problem that's going to be quite important in the next few lessons. So make sure you understand it. Let's take a look at what the problem says. In the diagram below, the measure of angle BAC equals the measure of angle DAC, right? These two angles are the same. I'm going to move this red angle out of there for a moment. All right. Based on the properties of rigid motions only, answer the following questions. All right, let's take a look. Letter A. If angle BAC was reflected across AC, if this angle, the red angle, was reflected across AC, then why must ray AB fall on top of ray AD? Consider what would happen if it didn't. So I'm claiming that if I take the angle in red and I reflect it across AC, then ray AB would have to fall on ray AD. Why does that have to be true? Think about this for a bit. All right, let's go through it. First, when angle BAC, and keep in mind what an angle is two rays. So I need to talk about both of the rays. When angle BAC is reflected across AC, AC doesn't go anywhere. Let's take a look at that. Let me actually do that reflection. I'm going to take this thing and I'm going to flip it up, down. There we go. AC didn't go anywhere. Why did AC not go anywhere? Well, it didn't go anywhere because point A is on the line of reflection and point C is on the line of reflection. And when a point lies on the line of reflection, when reflected, they stay put. All right, but now the bigger piece. Why did ray AB flip over here and land on ray AD? Well, it's this simple. Since angle measures are preserved, whoops, nope, let's try that, are preserved, AB, ray AB, must fall on AD to make the measure of angle BAC equal to the measure of angle DAC, right? Amazingly important. Now, I want you to really get this argument. This is critical. If I've got two equal angles that share a ray, when I reflect one angle across that shared ray, that ray must fall on this one. And it must fall on that one because if it doesn't, then the two angles couldn't have had the same measurement to begin with, or a reflection didn't preserve the angle measurement. And yet reflections are rigid body motions, and rigid body motions preserve angle measurements. So this ray must fall on that one. The second part of this problem is equally as important. Let's take a look at it. Under the same reflection, would point B have to land on point D? Use tracing paper to see if it does in this diagram. Under what circumstances would this have to occur? All right, so now this is different than letter A, right? Letter A is just, does this ray, this pointy thing, when I flip it down, does it lie along here? And the answer is yes. But now the question is, does this point B have to land on this point D? And you can already tell, if we kind of look at it closely, this is where point B went to when we reflected it over, and it didn't land on D. Now, why was that true? Why didn't B land on D? All right, and let me first just say the answer here is no, right? No, it doesn't, okay? And the key to understanding when it will is also understanding why it doesn't here. And why it doesn't here is very simple. It doesn't because AB doesn't equal AD. In other words, the length of that line segment, AB, is not the length of AD. But if AB, come on, move up the screen. If AB does equal AD, then B would map onto D. Pause for just a minute, not the video that is, don't pause the video, just pause for a minute to understand some ways that we talk about geometry. Right? We'll often talk about a point mapping onto another point, or a triangle mapping onto another triangle. And what that literally means is, you know, if this point B had been, this had been B, not this, and this distance had been this distance, then when I reflected across that ray, that shared ray, B would have fallen on top of D, and we say that B would map onto D. All right? Kind of neat. An important result. Again, when we reflect an equal angle over a shared ray onto another equal angle, the non-shared rays will coincide, they'll overlap. 2 points on those rays will then map on top of each other if they're both the same distance from that vertex. Really an important result. All right, let's wrap up this lesson on reflections. Right? Reflections were the second type of rigid body motion that we've seen, the first type being rotations. Reflections have the same sort of general properties as rotations, i.e. they preserve the length of the line segment and they also preserve the angle. But they're different in the way that they're carried out, right? The idea of reflecting a point in a line segment is very simple. We flip it over the line segment so that when we connect it to its image point, A and A prime, that line segment is perpendicular to the line we're reflecting across. The other piece is, of course, that the distance that the pre-image point is, the original one is, from the line of reflection is the same as the distance the image point is. Okay? Make sure that you know the general definition of what makes up a reflection and how to do it. Even though you might do a lot of them in the coordinate plane, you also need to simply know what a reflection is and how to mathematically carry one out. All right, let me just say for now, thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking, and keep solving problems.